of an atom. Planck's quantum theory. The animation here shows diffraction. Planck's quantum theory. Some of the experimental phenomena, such as diffraction and interference, can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of the 19th century physics known as classical physics. Number 1. The nature of emission of radiation from hot bodies, that is the black body radiation. Number 2. Ejection of electrons from metal surface when radiation strikes it, that is photoelectric effect. Number 3. Variation of heat capacity of solids as a function of temperature. And number 4. Line spectra of atoms with special reference to hydrogen. The animation here shows the phenomena of interference. According to Planck's quantum theory, when solids are heated, they emit radiation over a wide range of wavelengths. For example, when an iron rod is heated in a furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. In terms of frequency, it means that the radiation emitted goes from a lower frequency to a higher frequency as the temperature increases. The ideal body, which emits and absorbs all frequencies, is called a black body, and the radiation emitted by such a body is. The graph shows the wavelength intensity relationship. Here the y-axis shows the intensity and the x-axis shows wavelength lambda in nanometers. The graph is drawn for two temperatures T1 and T2, where T2 is greater than T1. The exact frequency distribution of the emitted radiation, that is, intensity versus frequency curve of the radiation from a black body, depends only on its temperature. At a given temperature, intensity of radiation emitted increases with decrease of wavelength. It reaches a maximum value at a given wavelength and then starts decreasing with further decrease of wavelength. Planck suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner, a belief popular at that time. Planck gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum of radiation is proportional to its frequency nu and is expressed by the equation E equal to h nu. The proportionality constant h is known as Planck's constant, and it has a value equal to 6.626 into 10 to the power minus 34 joule second. Planck suggests the animation shows the photoelectric effect, where we can see electrons are emitted by a metal surface when light energy falls on it. Number 2. The number of electrons ejected is proportional to the intensity or brightness of light. Number 3. For each metal, there is a characteristic minimum frequency nu naught, also known as the threshold frequency, below which photoelectric effect is not observed. At a frequency of nu greater than nu naught, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with increase of frequency of the light used. The values of work function W0 for few metals are shown. Photoelectric effect. Scientist Einstein in 1905 was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. When a photon of sufficient energy strikes an electron in the atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. The equation h nu equals h nu naught plus half mv square, where me is the mass of the electron and v is the velocity associated with the ejected electron. Dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the blackbody radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomena of interference and diffraction. The only way to resolve the dilemma was to accept the idea that light possesses both particle and wave-like properties. The following visual shows the atomic spectra. When white light passes through a glass prism, it is broken into 7 different colors, ranging from violet to red. It is called the white light spectrum. Evidence for the quantized electronic energy levels. Atomic spectra. The speed of light depends upon the nature of the medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than the one with a longer wavelength. Ordinary white light consists of waves with all the wavelengths in the visible range. A ray of white light is spread out into a series of color bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has the shortest wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.5 into 10 to the power 14 Hz to red at 4 into 10 to the power 14 Hz. Such a spectrum is called continuous spectrum. When the beam of white light is passed through the prisms as shown, then you can clearly see when it passes through the first prism, it is broken into 7 different colors, which is again joined to form the single beam of white light when it passes through the second prism. Evidence for the quantized electronic energy levels. Line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atoms produced emit Electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. Balmer showed in 1885 on the basis of experimental observations that if the spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the following formula. Nu bar is equal to 109677 into 1 by n1 square minus 1 by n2 square centimeter inverse. The series of lines described by this formula are called the Balmer series, where n1 equals 1, 2 and so on, and n2 takes the values n1 plus 1, n1 plus 2 and so on. The value 109677 centimeter inverse is called the Rydberg's constant for hydrogen.